Hi, my name is Gilbert, and we are Group 3 Mission Control. Welcome to our presentation on our last assignment.
Hi, my name is Aksh Patel. I was the project manager for the first assignment, and I'll be briefly explaining what we did and what our results were. To ensure an objective, strategic project selection process, we used a constrained weighted factor model, a more sophisticated version of the standard weighted factor model. This model allows us to evaluate and compare potential configurations for our vessel using a structured quantitative approach. First, we identified key evaluation factors based on both our project goals and client priorities. These included build cost, operational cost, performance for / maneuverability, workspace / storage, durability, and reliability. Each of these factors was assigned a weight to reflect its relative importance in our overall decision making. What makes the constraint model unique is the use of threshold values, a minimum acceptable score that each project factor must meet before its weighted score contributes to the total. For example, if a design scores below the safety threshold, its entire contribution to the overall evaluation is removed. This ensures that no project can be selected fails to meet the baseline requirements in critical areas like safety or regulatory compliance. This method helped us eliminate low performing or non viable options early and confidently move forward with the vessel design that best balances performance, safety budget, and delivery goals. By using this model, our final selection wasn't just the highest scoring, it was also the most aligned with the project success criteria. As you can see on the table, we have our top 3 combinations and what they scored. And as you can see, the first position was a 36-foot aluminium hulled twin engined half cabin design. And on the right, you can see the equation we used to calculate that said final score.
Hi, this is Pelumi Alamu, and I was the project manager for the second assignment about project organizational structures. There are 4 types, but we focused on 2 for the project. For the startup company, we selected a pure project structure to manage the vessel development because of the need for full-time commitment and maximum flexibility within our team. This is the diagram showing the functional departments and the group members that head each of them. We have Tolani for R&D, Gilbert for finance, Farha for marketing, Aksh for manufacturing, myself for management, and Quill for legal. The president position is currently to be announced. So the following are the reasons that we chose this structure for the startup. First, it gives a dedicated workforce that's focused entirely on the project. Second, communication is clear and fast because everyone reports directly to the project manager. Third, the structure is simple and flexible, which makes it easy to adapt as we grow. Next, it supports a more holistic approach to the project, and this way we're able to align all efforts towards the overall goals. And finally, it enables rapid decision making. The second structure is the matrix structure, which blends the strengths of both functional and pure project models. It can lean toward either side or stay balanced between the two. We kept the same group members as department heads, and the numbers in the diagram show resource allocation, combining full and part-time employees, which is why some of them are decimals. The resource distribution varies depending on the project. For example, Project 1 involves mass production of past vessels, which means it requires more attention from manufacturing and quality teams with no input from R&D. Project 2 focuses on R&D for new vessels, so the R&D department has the largest presence. And lastly, Project 3 centers on marketing and sales, so that explains why the marketing team has a higher allocation. So we chose this structure for many reasons. First, it allows efficient resource allocation. It provides access to specialized expertise. It offers job security and continuity. It maintains consistency in practices and remains flexible because the functional units can adjust support as needed.
Hi, it's Gilbert again, and I was the PM for this assignment. The bill of materials represents a comprehensive inventory of all the components required to construct the vessel, organized by major systems such as hull, construction, propulsion, electrical, and others. As shown on this slide, we've included a view of the BOM for one system, in this case the freshwater system. This gives us a clear example of how each component is documented with quantity, unit, cost, total cost, description, and source. By carefully specifying each component, we ensure the design meets the performance and operational standards required by the Texas Park and Wildlife Department. Similar tables were also developed for every system in the vessel. On this slide is our master summary, which compiles the total cost for each major system, allowing us to track spending across the entire project. The total material costs came to $200,770. Beyond cost tracking, the BOM was foundational to our planning process. It directly supported us in identifying our activities for our work breakdown structure, linear responsibility chart, and Gantt chart.
Hi, this is Fariha Kobetosha and I was the project manager for assignment 4, which was work breakdown structure, linear responsibility chart and Gantt chart. We applied a system-based work breakdown structure to divide the project into major systems like hull, anchor, propulsion and more. Each system was broken into subcomponents and tasks, resulting into 68 work packages, each clearly defined for scheduling and responsibility. Next, we created a linear responsibility chart. Roles were categorized into 4 levels: primary, secondary, approval, and review. This ensured that every task had a clear owner and support structure, reducing confusion during execution. Finally, we built a Gantt chart by assigning start date and duration to each work package. We maintain logical task sequencing and enable parallel workflow while respecting critical dependencies to keep the project timeline efficient. For example, we made sure that the planning comes first, then hull and deck building, and after that we went for electric system, sanitation system building, etc. After the system has been built, we do the sea trial, vessel modification, and delivery, which end by week 20. In total, we needed 100 days for that.
Hello, my name is Quill, and I am the project manager for Assignment 5, Project Budgeting. To estimate our project costs, we used a bottom-up budgeting approach based on our work breakdown structure. Each team member provided input for their respective tasks, which we then costed based on estimated hours and labor categories: professional, skilled, and unskilled. To account for overhead, we applied a 10% indirect cost on top of labor costs. Direct labor estimates were calculated in man-hours per task, adjusted for inefficiencies like breaks and startup time. In addition, we added a 7.5 contingency buffer to cover uncertainty. Because our vessel has a repetitive welding task for the aluminum hull, we incorporated an 80% learning curve to model increasing efficiency. The estimated labor hours for this task was revised to better reflect realistic performance improvements over time. Our budget is structured as an activity budget, focused on classifying individual expenses as line item expenses and organizing them into each department.
My name is Talani, the project manager for the next assignment on Project Network. To help us develop a manageable and analyzable project schedule, we created a simplified network diagram, which we derived from our work breakdown structure. Instead of us modeling every single work package, which would have resulted in an overly complex network, we grouped related tasks into higher level activity sets. This allowed us to visualize the full sequence of work while keeping the number of nodes within a reasonable range. Making use of an activity on node format, we were able to structure the network to reflect logical task dependencies and durations flowing from left to right. Each node included expected activity durations and was labeled with calculated values such as the earliest start time, the latest start time, and the slack. To help us determine the critical path, we conducted a forward and a backward pass through the network. So the forward pass established the earliest starts and finish times, while the backward pass calculated the latest start and finish times without delaying the project. From these calculations, we were able to identify the critical path which is the sequence of tasks that have zero slack, which meant that any delay in these tasks would directly impact the total project duration. In our case, the critical path consisted of key activities that must proceed on time to meet the project schedule. This critical path is also represented on our network diagram using the red linkage. Our finalized network provided us an expected project duration of 123 days, and this gave us visibility into where flexibility existed within the non-critical tasks. This informed both our resource allocation and also our ability to manage potential disruptions.
Hi, this is Pelumi again, and I was a project manager for the next part of the assignment that was focused on project crashing. Project crashing is a technique that's used to shorten the project duration by adding extra resources, which is usually labor, and while it speeds things up, it also increases the cost due to the additional hiring and firing that's involved. The network diagram here is the activity on arc representation, and it shows the process under the crash schedule with the number of days shown at the bottom. The red arrows highlight the critical path, the black arrows show the non-critical activities, and the dashed arrows represent the dummy activities. On the right, there's a table that lists all the activities, their predecessors, the durations under the normal and the crash conditions, and the associated costs. When deciding how much time to reduce from each activity, we use practical judgment, mainly considering how the tasks depend on each other and basically how it affects the overall timeline. We prioritize crashing the tasks on the critical path with the lowest cost first to get the most efficient time savings. And although the table includes crash costs for all tasks, we only crash the critical path activities in red, and this is because crashing non-critical activities doesn't really make any difference. That gave us a total crashing cost of $14,500, and it cut the project timeline by 30 days. Here we see a clear comparison between the labor costs under the two project timelines, and it's clear that project crashing leads to an increase in the costs. After crashing, there's a total cost difference of approximately $14,500 between the normal and the crash schedules. The hiring costs were calculated at $1,000 per skilled worker and $500 per unskilled worker, while the firing costs were based on 30% of the total hours worked. Since the total hours remained the same, firing costs did not change between the two schedules, and as mentioned earlier, applying crashing reduced the timeline by 30 days, which is a meaningful reduction in the project duration, although it came with additional costs.
Hi, it's Aksh again, and I was the project manager for this assignment. In this assignment, we leveled our original schedule in an attempt to reduce our costs of employment and thus reducing total costs. This was done by grouping similar activities together, as you can see highlighted on the table in different colors, in which yellow represents hull and related activities, blue represents electrical and related activities, and green represents freshwater and sanitation. The grouping was done based on the most similar activities being grouped together, which would allow for the same worker to take part in all the activities that are part of that specific group. This would allow for a reduction in hiring and firing costs. The grouping also helped as similar working skilled and unskilled employees would be kept hired for the most part until they have completed their part and only then be fired. Once the leveling was complete, we calculated the new total value for employment costs. We then compared level costs to the original costs to see the changes that had been made to our budget after leveling. The results are as follows. For our original schedule, the total labor costs ended up at $230,460.02, whereas once leveled, the total labor costs had dropped to $224,847.
In conclusion, our final vessel design is built on our winning bid configuration, a 36-foot aluminum hull with a half cabin and twin diesel engine design. Our comprehensive planning and meticulous component selection have culminated in a total project budget of $454,244. We have also structured our schedule to ensure vessel completion and delivery within 123 days. Overall, this configuration not only meets the performance and design requirements, but also meets the project's deadline and budget parameters. Thank you for listening to our presentation.